Alright, Logic fans, welcome back to our third video on 6.11 Identity Substitution. We're exploring the intricacies of this new identity rule and sort of syntactic rule, and this is about as advanced as things get for us in the course. So let's look at another example here, and in this case, we've got a really interesting idea, which is, the first premise says A has the property F. The second premise says B lacks the property F. So, for example, this says A is red, and this says it's not the case that B is red, right? And they conclude from that therefore A is not B, where the idea is supposed to be that if A were identical with B, then they would either both have to be red or neither of them could be red, right? If they were the same thing, they would have to have the same property here. And since the premises indicate that they do not have the same property, they cannot be the same thing. So intuitively, this is a valid argument, but our job is to syntactically deduce the conclusion from the premises, thereby demonstrating that it is in fact a syntactically valid argument. So I've got you started here. Your start is going to look like this, and I'm going to give you a little bit of a hint here. And since you're trying to demonstrate numerical diversity, that A is not identical with B, in this case, a common technique, doesn't have to be used, but a common technique is to use indirect proof. Okay, so I'll give you, I'll flush that out a little more as a second hint in a second, but just with that, pause now and see if you can't crack this problem. Okay, so here's your hint, flushed out in a little bit more detail. Since you're trying to prove that A is not identical with B, assume that A is identical with B for indirect proof, and that's our assumption. And now you're just looking for a contradiction, okay? And this is the common technique used to prove numerical diversity. So pause now and see if you can finish it from here. Okay, hopefully you're able to get this, but you're going to bring everything to bear. You're going to use indirect proof, and then you're going to use identity substitution. So here's the idea. Once you've assumed that A is identical with B, you can use these and this to get identity substitution. So, for example, on 2 and 3, you can get it's not the case that FA. And now you've got both FA and not FA, right? And you could have done it and gotten FB and not FB as well. But here we've done it this way, right? So we conj those together, and now we've got an explicit contradiction, something of the form P and not P, where P has the value FA. Okay, so having obtained what we wanted, we discharge this assumption. We write down that assumption, the first thing we assumed, arrow the last thing we got, which is our contradiction, and then everything follows the same format as before, no changes. LNC, modus tollens, A is not identical with B, QED, and what a lovely way of demonstrating numerical diversity. Okay, so let's look at a couple other issues involving identity substitution. And again, you're going to have to go through the practice problems, but one question I get all the time is, Ash, how does identity substitution work with relations? So I've designed this exercise to get you feeling comfortable with that, and then we'll do one more last problem involving relations so that you can really feel comfortable with it heading into the exercises. Now, the question is which of these applications, each of these allegedly involves a legitimate use of identity substitution, and the question for us is, are these alleged legitimate uses of identity substitution in fact legitimate, permissible, or impermissible? Okay, so pause now, run through these, and we'll come back and do them together. Which of these are permissible and which of these are impermissible? Okay, so hopefully you've had a chance to pause and work through these, but let's go through these together. And A here is absolutely permissible. You can do this. This is fair game, okay? And you only have to replace one, and that's fine. and even if the A is identical with B and B is identical with A were written in different ways, it would still be absolutely just fine. Could you have replaced the first one instead? Absolutely. Could you have replaced all of them? Absolutely. A, B, C, D are all permissible. Feel free to use those. All right, let's go ahead and take a look at E. Does the negation here change anything? No, it does not. E is permissible as well. You are absolutely allowed to do that kind of thing, okay? So it's just sort of making explicit all the allowances and prohibitions of identity substitution here. What about with this case? Can we go ahead and do this? And the answer is no, you cannot do this. You replaced an individual constant as opposed to an individual variable or pseudonym, and so this is impermissible, criminal, illegitimate. Do not do it. Okay, let's take a look at case G. Is this okay? And yes, this is absolutely just fine. You replaced the individual constant here with this one using that, and that is absolutely fine. All right, let's go ahead and take a look at the final case H. Double A, B, C. A is identical with B. So you get BB, AC. This would be impermissible. Do not do it. Replacing all the A's with the B's is absolutely fine, but then turning around and replacing the B with the A at the same time, it's only one type that can be replaced at a time. So you could go ahead and do this, obtain this same result by using two applications of identity substitution, but not just using one. Okay, and that's the basic of relations. So let's take a look at an example where you might have relations and identity involved. Okay, so this last one's a bit tougher. Okay, it involves relations, identity substitution, and indirect proof. Okay, so you're going to be trying to prove numerical diversity, that there's at least two things, right? And your evidence for that, the givens, are that at least one thing bears the relation R to B, and it's not the case that C bears the relation R to B, so there must exist at least two things, okay? Go ahead now and see if you can give this a try. We're going to do it together. I'll give you some hints along the way, but for right now, using just what you've learned so far, pause and see if you can't figure this one out for yourself. Okay, here's your first hint. Reverse engineer the conclusion. This is the desired conclusion. If you were to reverse engineer it, right, here it is here. You know, imagine it stripped of its quantifiers. What does it look like? It looks like something like that. So you're trying to get from these two things, from your premises, to something that looks like this, which again is a numerical diversity thing, and we use IP for that. So with that hint, right, you're trying to get from these to this thing. You might have to use IP. Go ahead and pause now and see if you can't figure it out. Okay, I'll give you another little hint here. Remember a strategy from before. You should existentially instantiate as soon as possible, always, right? So let's existentially instantiate this first, and we get Rvb. Alright, so from not Rcb and Rvb, we want to get something that looks like this. So how do we do that? Well, let's assume that we didn't have that. So let's assume we had V is identical with C, right? And notice the relationship here, right? If V is C, then you would have a contradiction, right? You would have not Rcb and not you would have Rcb and not Rcb. So that's the sort of tip-off there. So can we go ahead and solve this problem from there? Pause now. Okay, and hopefully the way forward now was fairly clear. So you instantiated this, right, and you got Rvb, right, and then you know you had not Rcb. So if you had a relationship between V and C, you could get a contradiction easily. So assume V is identical with C, right, and then you can get your Rcb, and then of course it's just a matter of conjoining together your contradiction, Rcb and not Rcb, and from there you discharge your assumption, right, law of non-contradiction. then you get your modus tollens, and now that you've got this construction, which is something roughly like this, right, it's just a matter of building from this up to something like that. And of course we're able to do that by existentially generalizing and in the correct order, EY first, then EX, and you finish your syntactic deduction that way. And what a really nice way of being able to demonstrate numerical diversity. All right, logic fans, it's been good. Look forward to seeing you on our ultimate study 6.12, where we will investigate theorems of logic with identity. You'll see some really cool results there, and I hope to see you there.